these are the notes for section 4.2, and section 4.2 is solving the absolute value equations. And let's talk about some definitions first. So absolute value, we know absolute value by the symbols of the vertical lines on either side, an expression or a number. And we know that it takes whatever is on the inside and makes it positive. And so this represents then a positive number. And so when we talk about positive numbers, a lot of times we talk about distance. So the absolute value then, that as far as the definition goes, is that distance from zero. So in other words, if we would look at a number line, right, and we would be out here at some location, I'll call it little d, then we are a distance of that length from zero. But we could also be a distance of the same length away from zero on the other side, which means we could be at negative d. And so what happens then is we end up having two possible locations for acceptable answers, right here or right here. And so absolute value then tends to lead to two unique solutions. We talked about equations in the previous unit. We're going to have some inequality questions in this section, and so we just a quick reminder of what an inequality is. Inequality is when you are looking at expressions and they have these symbols, that's greater than or equal to, or less than and less than or equal to, and it really, those symbols are used to compare two numbers. So we are comparing the values. Compare values of two numbers. Okay, and whether or not they're equal to each other or less than or greater than. And so this leads to infinitely many solutions, excuse me, infinitely many numbers that would be solutions to the expression that we have. So I think in this statement, why are there usually two answers to an absolute value equation? We kind of covered that just a second ago. There are two distances from zero. So we kind of covered that by talking about this. There are two distances from zero. Okay, so looking at this first example then, what we are saying here is we have this expression, it's 2x minus 5. And we're saying 2x minus 5 is a distance of 9 from 0. So what x satisfies that? What x would satisfy making that distance 9 from 0? And so our solution strategy then is to kind of think of the fact that 2x plus 5 is either going to be a distance of 9, or that 2x plus 5 is going to be at a location of negative 9. So we're looking at that. So we're setting up two scenarios. 2x minus 5 equals 9, or 2x minus 5 could end up being the value negative 9. And then because it's on the inside of those absolute value signs, it would just be, we would take the positive value of that answer. And so what we're doing then is we're saying we could have either one of these solutions. So now it boils down to those solution strategies you learned in the previous section. So we're going to add 5 to both sides. Then we'll have 2x equals 14, and then we're going to divide by 2. And so we could be at 7. X could be 7, and if x were 7, if we just look back up here, 2 times 7 is 14 minus 5 is 9. So that gives us our positive 9 inside the absolute value signs. Or if we solve this one, notice I'm adding 5 to both sides. I am doing the same steps that I am doing over here. There's nothing new about these steps because the expression is the same on the left-hand side. So just to kind of, you know, if you're struggling through this solution strategy, once you make it through successfully, we just have to duplicate it over here. However, this right-hand side, since the right-hand side is different, right, we're going to end up having a different number over here. So minus 9 plus 5 is minus 4. Divide by 2, and x equals negative 2. So negative 2, when we plug it into here, negative 2 times negative 2 is negative 4. Negative 4 subtract 5 is negative 9. And then we can take the absolute values of that and get positive 9. So those are our two solutions for that problem. Example 2 is an inequality. So really similar setup, as you can see. I've got an expression here. In fact, it's very similar. It's 2x plus 7, so really similar, and is less than now 11. So this is going to represent a whole family of solutions on the number line. And so this is when we start typically drawing a number line to represent our solutions. Just to kind of get a picture of that. Before we go to that example, as long as I'm talking about drawing a number line, the solution on the number line for this example would look like this. We would have two solid dots, one at negative 2 and one at 7. Equalities lead. This equality is going to lead to one single correct answer, and this equality is going to lead to one single answer, so there are two solutions. Inequalities, we get infinitely many solutions because we now are starting to occupy parts of the number line. So taking a look at example 2, the setup is the same. We're going to say this expression 2x plus 7 can have a value of 11 because taking the absolute value of that would still lead to 11. Or this expression 2x plus 7 can have a value of negative 11 because, again, we've got the absolute value signs there, which would make it positive. And then we're going to go through our solution strategy. So we know we're subtracting 7 from both sides. And so 11 take away 7 is 4. And when we divide by 2, we get 2. And then the other side, oh, I made a big mistake here. Hold on here, right? I before I correct it, right, I need this inequality here. Totally forgot about that. Really common mistake. I like to leave by those common mistakes in my video. So I'm going to get rid of that and get rid of all these equal signs. And I am going to get my less than sign. And then we got to talk about the other solution. Put my less than, oh, well, let's talk about the other solution. Put my less than sign here, so I put my less than sign here. So this solution says x is less than 2. So that's an acceptable, any value less than 2 will satisfy this equation. So 2, let's plug in 2 here. When we plug in 2, 2 times 2 is 4, plus 7 is 11. Absolute values of 11 is 11, and 11 is not less than 11, so 2 is not going to work, but less than 2 will work. So let's try 1. 2 times 1 is 2, plus 7 is 9. Absolute value of 9 is still 9, which is less than 11, so that's a true statement. Same with 0. We could try like 0.5, that would also work. Okay, let's talk about this one. So the other part of the solution, because there's this inequality here, I'm going to change colors, because we're saying, hey, this expression could be a negative value. What we just did is we just switched this from being a big number to a small number. And so when we do that, we also have to switch the sign. So instead of less than, we use a greater than sign. We're switching the magnitude of the value, so we have to switch the direction of that inequality. And I'll get more into that as we solve this. So I'm going to go back to purple. I'm going to repeat my steps. I'm going to subtract 7 from both sides. And we have 2x is greater than negative 18. And then divide by 2. And we have x is greater than negative 9. So basically, making that sign on the 11 negative is saying, basically, we're flipping ourselves to the other side of the number line. And when we flip ourselves to the other side of the number line, then basically we're saying take a big number, make it little, which means little numbers become big. So we have x is greater than -9. So let's take a look at the number line here and try this. Here is 0. Here is -9. Greater than -9 are these numbers, right? Bigger than is on the right side. So if we tried something like -5, right? I'm just going to write in gray here. If we tried something like -5 and put -5 up here for x, then we would have 2 times -5 is 10, is -10, plus 7 is -3, and -3, absolute value of that is +3, which is less than 11. So if we would have kept the less than sign, we would have been talking about this stuff. And this stuff, as you can see, is farther away from 0. That's why that sign had to flip, because we needed to be less than 11 away. And everything over here would put us farther away. So that's the really important idea as to why that sign has to flip. Okay, so x is greater than -9. Since we have strictly greater than, we know that -9 won't work. So that's where the open circle comes from on noting the solutions on the number line. And then we say, and then we shade in everything that is greater than -9. Going back to our first solution, x is less than 2, same sort of idea. Here's 2. Here is here is 2. We know 2 didn't work, so it's an open circle, and we got this less than 2. So if we notice, we've got these 2 different solutions, but we can only occupy where the portion of the number line where they both work. And the portion of the number line where they both work is right in here. So on the number line, we would write that solution as something that looks like, let me change colors here again, open circle at -9, open circle at 2, and shade everything in between. So that would be the total solution. And we could write that also as an inequality that's compound. So that's the one that it has a couple inequalities in it. So we start with the little number, -9, and we know x is greater than -9, or in other words, -9 is less than x, and x is less than 2. So we could write the solution set like that. The solution set's written individually like this don't really tell the whole story, because we can't go, like this one will go beyond 2, and that's not allowed. We can't go beyond 2. And this one will go beyond -9, and we can't allow that. So these are not acceptable answers by themselves. Okay, so let's take a look at example 3. So example 3 is just like example 2 in the idea, okay, in the idea of 2 solutions, flipping the sign, looking at the number line and seeing what's going on, okay? It's just that we have this equal to sign here, and the only thing that changes is that it takes these dots and it closes them up, just like our example 1, right? Okay, we had an equal to sign up there and we colored in the dots. Okay, so looking then at example 3, we've got 3x minus 2. That expression could be greater than or equal to an 8, or that expression 3x minus 2 could be less than or equal to a -8. I'm going to go ahead and solve this. So I'm going to add 2, and I got 3x is greater than or equal to 10. Divide by 3, and I've got x is greater than or equal to 10/3. I'm just going to leave it as 10/3. That's 3 1/3. Okay, right, 3 goes into 10 3 times with 1 left over, just so that I know about where to put it on the number line, although I don't really draw my numbers anyway. Okay, same steps, add 2 to both sides. Get 3x over here, less than or equal to, right? I flipped that sign because I changed the sign out here. So that's kind of how I remember it without thinking too much about it, is if I change the sign here, or if I change the sign here, I've got to change the sign here. That's kind of how I remember it, without going into that big elaborate explanation that I did before. And this is -6. Remember, different answer out here because we had a different sign. Divide by 3. X is less than or equal to -2. Okay, so a quick number line solution here. We've got 0, we've got -2, and 3 1/3 is a little bit farther away. 3 1/3, or 10/3, you can call that. So x is less than or equal to -2. Less than or equal to means solid dot, and this way, littler means to the left. And greater than or equal to 3 1/3 looks like this. And so this is a situation where I can be in either of those spots. And it will be, so if you think about this in real general terms, we're talking about distances greater than 8. So if my x values are here, greater than means farther away. So I have to be farther away from those values in order to be farther away from 0. And likewise here, greater than means being farther away. And so we just take those answers as our solution. I could be here, literally here, or here. Those are the ones that we don't have to put together. Okay, so a couple of word problems. And the word problems are kind of interesting. They're not too bad if we kind of look at them in this way. So we're writing a model. And it's always difficult to come up with the equation, right? There's a lot going on here in these word problems. But we want to write a model. And so we have the cereal manufacturer has a tolerance of 0.75 ounces for a box of cereal. So what does that mean? Well, that means we don't have to be exactly the weight that it says on the box. You know, if you look at the bottom of a cereal box, it has the weight in ounces of the contents inside. And so if we have a 20-ounce box, we don't have to be exactly 20 ounces. But we have we have to be close to 20 ounces. And so this tolerance then is how far off can we be? So this is how far off. How far away? So this is the distance, right? How far away we have to be. So we can't be any farther away than that. We have to be closer than or equal to 0.75 ounces. So, but we could be on either side of it, right? So it says, write and solve an absolute value inequality that describes the acceptable weights for 20-ounce boxes. So if we just think about this conceptually, if I can be on either side of 20 by 3/4 of an ounce, so either side of 20 by 0.75 ounces, well, that just means that all I have to do is add or subtract 0.75 ounces from 20. Right, that would be on either side of 20. So our first answer would be 20 minus 0.75, which would be 19.25 ounces. Or my other one would be 20 plus 0.75, a little bit heavier, a little bit more cereal, which is 20.75 ounces. Okay, so so that would be a kind of a conceptual way of doing it. But let's write an absolute value model. Let's kind of get a strategy that we can use with any problem. So the tolerance, you know, like I said, kind of alluded to it here, the tolerance can either be plus or minus 0.75. So the tolerance, the wiggle room, so to speak, that we have is what's on the outside, on the right-hand side of that expression. So we have the tolerance, oops, and we've got to be within that tolerance. So we have to be less than or equal to that. And then in here, we're going to have the ideal or the selling weight, you know, the claim that it's 20 ounces. I'll call it ideal. The ideal weight. And then here's our variable. So it's the actual weight. And you've actually dealt with this in science, this sort of concept. And it would be like experimental minus theoretical, you know? It's kind of that sort of, so if we looked at this in general terms, it would be kind of like experimental minus theoretical, right? You've done that when you've calculated percent error in science. So it's kind of that sort of philosophy. Okay, so setting up this equation, then the actual weight is we don't know it, right? We don't know our actual weight. Minus 20 is less than or equal to 0.75, right? And then we would set up our two solutions. X minus 20 is less than or equal to 0.75, and then x minus 20, let me slide that over a little bit. X minus 20 is greater than or equal to negative 0.75, right? Change the inequality, change the sign here. And then we can add 20 to both sides, plus 20, right? That gets me this, right? Plus 20 in my conceptual solution there. And then we have x is less than or equal to 20.75, right? We said that was the biggest it could be. And then we repeat our steps here, plus 20, and that again is this right here, right? 20 minus, and then we have the x is greater than or equal to 19.25, right? It's got to be closer than 19.25 to 20. And so this is just like our first example on the number line, right? X is less than 20.75, x is greater than 19.25, so we're between those two values. So we should rewrite our answer, We should rewrite our answer that 19.25 is the smallest, and x has to be between that and 20.75 as our answer as an inequality. Looking at the last one, your quality control inspector at a bowling pin company, a regulation pin must weigh between 50 and 58 ounces. Right, an absolute value inequality describing the weights you should reject. So we don't want these pins too light, they would knock over too easily, right? We don't want them too heavy because then they won't knock over very easily. We want to make sure that they're really consistent. Bowling's really important. So we got to make sure that that's true. So, we're going to go back to this experimental versus theoretical, right? We don't know either one, but we do know that the lightest should be 50 and the heaviest should be 58. So in other words, comparing it to example 4, we know this information, the 19.25 and the 20.75. So what we need to find, we know that these are on either side of a middle value, right? And we also know that when we talk about, in fact, we could kind of do a number line scenario for this. We just have to come up with an expression, and the expression isn't bad. But let's talk about a number line scenario. I'm not even going to worry about 0 because we're way out at 50 and 58. But if this was 50 and this was 58, then what is right in the middle? And if you think about it, you know, they're 8 apart, so halfway would be 4. 54 is in the middle. That must be the theoretical weight. So if we want to write an absolute value inequality describing the weights, we would have our experimental or our actual weight, to use the verbiage from the previous question, actual weight. And then we would have our theoretical or our ideal weight. And then we're talking about writing something that is wanting us to reject the pin. So we have a reject would be anything out here or anything out here, right? The stuff that's too heavy or the stuff that's too light. That would be the reject. So we want the distance away from 54 to be greater than 4, right? So we want it to, so that must be our tolerance. So this is our theoretical value. Our tolerance must equal 4 because that's our distance. And so we want to be greater than 4. We want to be greater than, I'm going to have to put this somewhere else. There we go. Greater than the tolerance, if I just write it in general terms. And you don't have to go through all this explanation when you do it, but I'm just trying to give you a little background information. So that would be a good good inequality. Or if you wanted to make it specific, you could say the actual weight we don't know. It's from 50 to 58. The ideal weight is 54, and that has to be greater than 4. That would be also another acceptable inequality that would be specific to this problem. So those are the notes, and in your packet to follow are the solutions, and just another reminder again, these are the answers, so that you can have some immediate feedback and keep moving through the questions. Solutions will post in Blackboard a day or so after the assignment, or the day when the assignments due. So if you really